So now that we talked about covalent compounds and covalent bonds, and we can how we draw the covalent compounds using the Lewis structure model, let's try to now learn how to name covalent compounds. Okay, so what you're looking here on this slide, this is the binary covalent bond generic formula, right? And the word binary, what the word binary means, it means two. And of course, because we're talking about a bond, that means you need to have two elements or two atoms forming that bond together. So that is essentially what the word binary means. Um, when it comes to A and B, the elements, of course, those are nonmetals, and we talked about covalent bonds earlier, and we said how covalent bonds are formed between the nonmetals, which is the group right here in the light green in the periodic table. So nonmetals, that's something that we know about earlier. The subscripts down here, these subscripts, these number indicate the number of the atoms of that specific element in that molecular formula. So if there is one, that means there's one atom. If there's two, that means there's two, so on and so forth. Now, sometimes those numbers are absent. And I think I mentioned that before. If there is no number, you should always assume the number is one because number one is never written. Okay? So here's some of the common names for covalent compounds. I'm pretty sure you heard of all of these, if not all, probably most of them. For example, water, H2O, and it is a covalent, right? Because oxygen and hydrogen both are nonmetals. Same thing with nitrogen and hydrogen forming the ammonia. Methane, ethane, and propane, these hydrocarbons are also covalent compounds because carbon and hydrogen both are nonmetals. So the reason why we need to learn the rules and follow the convention, the UPEC convention, that's what it's called, when it comes to naming covalent compounds, because you will be running out of common names if we try to name all the covalent compounds with common names, and we'll be running out of space in our brain at the same time. So we need to find and we need to learn a common set of rules where we can just name any covalent compound without trying to memorize the common name of it. And that's what we're going to try to do today. Um, so naming a binary covalent compound, first what we need to do is we need to pay attention to the subscripts, okay, below every element when we're trying to name that specific compound. What we use, in this case, we use this table right here to indicate the number of atoms. So if there is one atom, we use the prefix mono. If there's two atoms of that element, we use the prefix di. If there is three atoms of that element, then we use a tri, so on and so forth. I will be giving you this chart in the exam hope to make things a little bit easier. But again, you'll have to learn how to use it, otherwise it will be useless. Um, so first, what we need to do is we need to use the prefix to indicate the number of atoms of that specific element. However, for the first element in the compound that we're trying to name, we never use the prefix mono. Okay? So for example, in this case, it's chlorine and oxygen. Because of chlorine, there is no subscript down here. We are going to assume the number is 1. And because of chlorine is the first element we're naming in this covalent compound, we are not going to use mono. We will just use the word chlorine. We will use the word mono for the second element, but not the first element. Okay? So there is no subscript after the first symbol. Please pay attention to this. Do not use the prefix to begin with a name. So we don't use mono. The name of the compound never begins with a mono. So our covalent compounds nomenclature never starts with a mono. Either starts with a di, tri, but never a mono. Okay? Now the reason why you see the O and the A between parentheses, because there are times where we will be dropping those letters if the element that we're trying to name starts with a vowel, something like oxygen and iodine. Okay? So we're not going to use, for example, mono oxygen. We use monoxide. Or we don't use tetra iodine or iodide. We use tetraiodide, so on and so forth. Okay? So let's go back, and since we have the chlorine compound here, this chlorine oxide, let's try to name this guy here. So first what I will do is I'm going to look at the first element that I have here. The element that I have is a chlorine. Is it 1 or 2 or 3 chlorine? No, it is only 1 chlorine, right? Because there is no subscript, so there is only 1 chlorine. Do I use a mono? No, I don't use a mono because mono is never used for the first symbol in the nomenclature. So my first element will be chlorine. How many oxygens I have? I have 2 oxygens. Di. And then we use the base, the root of the element, and we use IDE at the end. So it's chlorine dioxide. Okay? Let's look at the next slide. There is more details to follow. So you follow the prefix with the name of the first element in the formula, so that's chlorine. Then you write a prefix to indicate the subscript of the second element. Okay? So the second element is oxygen. So we use the prefix to indicate the subscript. The name of the element never precedes the prefix for the subscript. So we always indicate the number of that element, the number of the atoms for that element, before we mention the name of it. Okay? And this is one of the common mistakes people would do. And instead of writing dioxide, they write the oxygen first and then they write the prefix later. And that is a common mistake. Okay? Then you write the root of the name of the second symbol in the formula. And in this case, the root for the oxygen is ox. O-X. Okay? Then you add IDE to the end of the name. The roots of nonmetals, it's all listed. These are only the one that you need to worry about. These are the roots for the nonmetals. And yes, I will be also giving you this in the exam, so you don't have to memorize any of these. You will have it as supplemental data during your exam. But again, in the same time, you need to know how to use it, of course. Let's do another example. So let's follow the rule that we just talked about. So first, we need to note the subscript of the first element. What is my first element? It's nitrogen. Okay? When we're saying nitrogen, we see the number 2 next to the nitrogen. That means I have 2 of the nitrogen, correct? If we go back to our prefixes, for 2, we use di. So I will start with di, indicating the number of atoms for the nitrogen. Next, the name of that symbol, the name of that element. N is a nitrogen, so it is dinitrogen. So you follow the prefix with the name of the first element of the formula. So it's dinitrogen. Next, what I will be doing, I will also look at the subscript of the second element, which is 5. So I'll need to use the appropriate prefix for the subscript 5, and that will be a penta. Okay? So dinitrogen, pent, I'll be removing the A, right? Because A and O, and because the second element, the oxygen, the second symbol, the second element start with a vowel. So I'll be dropping the A from the penta. So it's a pent. The root for the element for the oxygen is ox. And you have it here in this table, right? So this is for oxygen. So it's ox, and we add IDE at the end. So you write the root of the name of the second symbol in the formula, and then you follow that with IDE. So all in all, this compound name is dinitrogen pentoxide, following the rules that we just talked about. All right, let's do more examples together. So let's try to name this one. So this one is chlorine dioxide, right? This is something that we just named in the first slide for naming covalent compounds. Let's do the second one. So the second one, I have bromine, right? That's the element from the periodic table. How many do I have any numbers next to the first element? No. So then the prefix for this subscript is a mono. But because I'm talking about the first element in this compound, we never start with a mono. Remember this. So it starts with just the name of that element, which is bromine. Next, what I need to look at is the prefix or the subscript next to the second element in that group, in that compound, which is 3. 3 is a tri based on the prefix for that subscript. Okay, so bromine tri, and then the root for the fluorine is a fluor, and we follow that with IDE. Now this might seem a little bit overwhelming, especially with the names of these elements, but again, you have to remember that you will have all the roots for the elements that you need to worry about. Okay, so if you're ever unsure what is the name of that compound, you just have to refer to the roots of the nonmetals, and that should take care of that. Okay, let's look at the next compound, which is methane, right? This is the common name that we just looked at, the methane. If I try to rename it, if I try to give it a name following the IUPAC convention, so first, carbon, right? That's the name of the element, carbon. There's only one. There's only one carbon in this compound, so it's a mono, but I'm not going to use a mono, right? Because it's the first element. Now moving on to the next element, which is hydrogen. Next to the hydrogen is 4. So the prefix will be tetra. And the root for hydrogen is hyd, hydra. And then we add IDE at the end, so it's hydride. So it's carbon tetrahydride. Okay. As I said earlier, one of the common mistakes, people would always name the element before naming and using the prefix for the subscript, and that is just incorrect. I think people, they're just going automatically by the sequence of the elements in the formula. Okay, but we shouldn't do this. We always indicate the number of the atoms, and then we follow that with the name of the element. Okay, just pay attention to this. The next compound that we have is bromine, right? There is only one subscript, so we're not going to start with a mono. Bromine, and it's a monochloride because there is only one chloride. There's only one chlorine atom, right? So it's a mono, and chloride because it's chlor followed by IDE. This is another name for water. It's dihydrogen monoxide. Okay, dihydrogen because there is 2 hydrogens, right? So that's di, and in this case we are using the prefix because it's not a single hydrogen. So it's dihydrogen, and oxygen because it's the second element. We will use the word mono in this case. It's monooxide. Okay. So in the exam, you might see it. You might see it both ways. Actually, you will see it both ways. I will give you the compound molecular formula, and I expect you to write the name for that formula, and I will also give you the name, and I would like you to write the compound formula. So you'll see it both ways. I'm going to try to give you both also on the practice problems, so you guys become more comfortable doing these problems. All right, let's write the formula for this. Okay, so it's chlorine monofluoride. So chlorine, we all know chlorine from the periodic table is Cl, right? Chlorine. Mono means it's a 1 of the fluoride. And looking at the root of the covalent of the nonmetals for the covalent bond, you can tell that fluor stands for fluoride, for fluorine. So it's from the periodic table, it's F. So it's 1 chlorine and 1 fluorine. So it's chlorine monofluoride. And this is the way that it's written. The next one is tetraphosphorus heptasulfide. First, what I would say, please don't panic from reading the name. Just follow the rules that we just talked about. Look at both tables that you'll have in the exam, and it's really just a matter of solving a puzzle, if you want to say. So it's very easy if you follow the rules. The names might sound intimidating, but it's really not that complicated. So tetraphosphorus heptasulfide. So when we say tetra means a 4. Phosphorus is a P, so we start first with the element. So Now we're doing it the other way around. We use the name, we put the name of the element first, which is phosphorus, and we follow that with a subscript, prefix for that subscript, or the subscript, it's a 4, and the heptasulfide. So we have sulfur, and then we have 7, indicating 7 atoms of sulfur. Iodine, monochloride, same thing, iodine, it's I. Monochloride, that means it's 1 chloride or 1 chlorine, so it's ICl. Okay, so that should take care of the covalent bonds, concepts of covalent bonds, and also drawing the covalent bonds when it comes to using the Lewis structure, and also the naming of the covalent bond. Now, let's get into the ionic bonds. I will also be posting another video with the practice problems for the covalent bonds. I'll do some practice problems and some examples to give you guys a better idea, especially for the Lewis model, on how to draw the Lewis structure model for covalent compounds. Now let's talk about ionic compounds. Okay, so now that we talked about covalent compounds and covalent bonds, let's now take a look into ionic compounds and see how the ionic bond different from defined differently than the ionic bond. First, when it comes to ions, if you remember when we talked about covalent bonds, we said the key word was sharing, correct? In this case, when we're talking about ionic bond, I would like you to pay attention to this word, which is transferred, fully transferred. So instead of sharing of electrons, electron in this case will be fully transferred from one atom to the other. When this happens, you have one atom that lost electrons, so it will have an X number deficiency of electrons, and as a result will have more protons, and another atom will have more electrons than protons. So the atom that has more protons than electrons will have a positive charge, correct? Because the protons are the positively charged particles. And the atom that gained these electrons will have more negative charge, more electrons, okay? So in this case, that's what we call cations and anions. So cations are the positively charged particle, and those are the particles that actually lost electrons. And some people are confused because when we refer to cations with a positive charge, they assume that it's the particles that gained the electrons, but in fact it's the opposite. Anions, on the other hand, are the particles that gained and accepted that transfer of electrons. So it has a more abundance of electrons compared to protons. So we'll have a negative charge, and cations will have a positive charge. So cations and anions are the positively charged particles and are the negatively charged particles. The key word here for ionic compounds is the transfer, the full transfer of electrons from one atom to the other, okay? So the ionic compounds is the attraction between cations and anions. So once you have electron that's transferred from one atom to the other one, the positively charged particles and the negatively charged particles will start forming a bond. And that should make all sense, right? Because you have the positive charge, you have the positively charged particles, you have the negatively charged particles, and they come close to each other in contact, and that's where the bonds is formed. So the attraction between the two charges, the positive and the negative, forms the ionic compound. Okay, the ionic compound is stronger than a covalent bond. So all the compounds that forms the ionic bond, they tend to have, for example, a higher melting point, a higher boiling point if it is at a liquid state compared to the molecules or the compounds that form the covalent bond, because the bond between the positive and negative is much stronger than sharing of electron. Okay, so that's the second feature or the second characteristic of the ionic bond. The third one, which is the most important, I think, and that's how you can identify ionic compound versus covalent compound or molecular compounds. The ionic bond forms between a metallic atom and a non-metallic atom. Well, the question would become, well, how would I know what is metals and what is non-metals? This goes back to, I think, our last lecture, when we talked about the periodic table and how it is important to really know the elements from the periodic table. Remember, we talked about a group one, group two, the alkali metals and the alkaline earth metal. Those are the metals from the periodic table, and those guys, the carbon, the boron, the nitrogen, the oxygen, fluorine, and all the halogen down here, selenium, phosphorus, so on and so forth. All those guys are the nonmetals. So basically, the ionic bond take place between these two groups from the periodic table generally, and that's what we're going to focus on, and those folks from the periodic table. The elements on a group one, well, with the exception to the hydrogen, because hydrogen is not considered a metal. So group one and two, as well as the nonmetals in the periodic table. We will also maybe get some examples or do some examples for using iron and manganese and a krypton. But the chemistry for these, I'm not gonna bore you with the details because it's a little bit out of our objective here. But a group one and a group two definitely interacting with the nonmetals, the nitrogen, oxygen, fluorine, etc. Okay, so that's how you can identify the ionic compounds versus the molecular compounds or the covalent compounds, right? Because when we talked about the covalent bonds, we said that it takes place between the nonmetals, correct? So exclusively between those guys. When the group one and group two interacts with the nonmetals, then that's where the ionic bond occurs. Okay, so that's how you. This is how you can tell the ionic compounds versus the covalent compounds. Now, that is pretty critical, especially when it comes to solving the homework and as well as in the exam. Specifically, when you're trying to name those compounds, if you're not going to be able to tell which is covalent and which is ionic compound, it's going to be a bit complicated to have the correct naming and following the correct naming nomenclature in this case. Okay. So it happens between metals, right? The metallic atoms and the non-metallic atoms. When the electrons are gained and lost, it can happen in single, double, or triple. So it's either one electron, two electron, or three electrons are lost, or you can have one, two, three, three electrons are gained. So in this case, what you have, or what we will see later on with the examples, we will see cations that has one positive charge, two positive charge, three positive charge, or anions that has a minus one, a negative one, negative two, or negative three. Now, what I would like you also to see beyond when you're reading these negative charges and positive charges, that this specific cation will have more protons than electron, right? In this case, so we're talking about this guy here. So this one will have a deficit of one electron. This one will have a deficit of two electrons. This one will have a deficit of three electrons, or more protons and more protons by one, two, or three. Obviously, we don't gain or lose protons. We always do that with electrons. So that's why I'm trying to emphasize on electrons and not protons. In this case, you have one added electron, you have two added or two gained electrons, and in this case, you have three gained electrons. Well, I think a pretty simple question would be, well, who decide and what decide, and how it is determined if it is one electron that gets gained or two electrons lost. I mean, what is the chemistry behind this? This is all really depends on the octet rule. If you remember when we talked about the covalent bond, atoms always try to reach the octet rule, which is 8 number of electrons to reach the stability or the optimum stability of electron configuration. Okay, so what decide which element or which atom gains or loses electron, whichever element or whichever atom is closer to the magic number of 8. That's how the gaining and losing of electron take place. So I'll give you an example. So something like chlorine. So if you look at a chlorine in the periodic table, so if you look at the chlorine and fluorine, let's look at the fluorine from the periodic table. So fluorine has 7 electrons valence electrons, right? Because the group is 7 right here. So it has 7 valence electrons. It needs 1 electron to reach the octet rule, or the octet number of 8 electrons in the outer shell. So we have two options here. Either gain the entire 7 electrons and go down to the next subshell, or, lose the 7 electrons and go down to the next subshell with 8 electrons, or just gain a single electron and basically reach the 8th count of electrons. So it would make more sense to gain an electron in this case. That's why when you see the fluorine, the chlorine, the bromine, the iodine, all those guys, they gain electron to reach the octet number. On the other hand, if you look something at the sodium, so the sodium has only one single electron out in the valence shell. So it would be much easier for the sodium in this case to lose that single electron and then have the 8 electrons, 8 electron octet, the 8th count of electrons, and reach the octet rule, or reach the stability, right? So that's why you will see the lithium, the sodium, the potassium, the rubidium, cesium, etc. All these elements, they will lose an electron, always found losing an electron to reach the octet rule, or to reach the 8th count of electron. So those guys has a +1 oxidation state, that's what we call it, and these folks has a +2, which is a group 2. So something like beryllium, for example, or magnesium has only 2 electrons in the last in the outer shell, and in the outer orbital. So in this case, it's easier to lose these 2 electrons than trying to gain 6 more electrons, which is impossible to take place. So all group 1 and group 2, group 1 is always found as a +1, of course, with the exception to the hydrogen, and a group 2 always found with a +2. Fluorine and chlorine always found as a -1 when it comes to gaining electrons, because again, those guys, they just need 1 more electron to reach the noble, or to reach the 8th count of electrons. Okay, we will talk more in details about that one as well. So ionic compounds, substances composed of ions attracted to each other by ionic bond. So the electrons are gained and lost, positive and negative charged particles are formed, and then you have these 2 compounds bonding together, or these two atoms, bonding together. Okay, so this is how the ionic bond forms. A quick diagram. So when you look here, you look at the sodium, for example. So the sodium, just like how we looked at the periodic table a second ago, right? So sodium belongs to the first group of the periodic table. So sodium always loses an electron. Sodium never gains 7 electrons. It just doesn't happen. So sodium always loses 1 electron. So it loses 1 electron. Now, every sodium atom loses 1 electron. When this happens, the entire atomic structure of the cation, or of the sodium, basically shrinks, and it gets smaller. And the reason for that is because the positive charge, the dominance of positive charge in this case, it drags the electrons even closer to the nucleus in this case. So it's a reaction that happens by the atom, that every time it loses an electron, the proton, the dominance of the proton, positive energy, it drags the electron closer to the nucleus, so it makes it even smaller. On the other hand, when you look at the chlorine will gain that electron. The opposite happens in this case. Because of the gaining of electrons, now there is a large abundance, there is a larger cloud of electrons that is now surrounding the nucleus of the chlorine. Okay, so now the chlorine ion has gotten even bigger. So sodium, that's why the sodium is smaller, because of the positive charge of proton. It drags the electrons even closer, so the electron clouds are now closer to the nucleus. The opposite happened with the chlorine ion. There is more electrons, more than what the proton, or the positive charge of the nucleus, can handle, so now it's spreading out. if that makes any sense. So ionic compounds, so attraction, and once that happens, you have the positive and negative charged particles getting closer to each other to form the ionic bond. Again, remember, the electrons are completely transferred from one atom to the other. Sodium chloride structure, each chloride ion is surrounded by 6 cations, and same thing, every each sodium cation is surrounded by 6 anions, so it has this molecular ball and stick model. That's what we call it. So far we've been talking about monoatomic ions, and mono means a single or one of its kind. That's why when we call something like NaCl, it's a monoatomic ion, because there is one of the Cl, and one of the sodium. So there's two different kinds, right? So there's the fluorine and there's the sodium. Sometimes we call it, there's a chance that a polyatomic ions are formed, or polyatomic ions, in other words, form a ionic bond, or an ionic bond with metal. So it's a combination of a covalent bond molecule. So you have a covalent bond molecule that has an abundance of a negative charge, and it's willing to form an ionic bond with a metal. So the covalently bond molecule will basically behave like an anion in most cases and form an ionic compound with a metal. In this case, the charge collection of atoms are held together by a covalent bond. And in this case, we are talking about the covalently bond molecule itself. So there's a covalent bond molecule has an abundance or a large amount of negative charge, in other words, electrons. And these electrons, it's ready to be transferred to a metal to form an ionic bond. This is an example of polyatomic ions. We'll talk about the ammonium in a second, because it's the only positively charged polyatomic ion in this case. And if you look at the others, all those guys in here, those are covalently bond molecules, right? Because if you look at them, they're all made from nonmetals. You don't see any metals in here, do you? So all these are nonmetals forming a covalent bond. This negative charge you see in here, or these 2 negative charges, for example, or 3 negative charges, these will act as anions and interact with the metals, in other words, the cations, and form ionic compounds. And we will look at this in a second. Types of ionic compounds, it could be either binary. A binary means a single, right? A binary ionic, like NaCl, formed by a monoatomic cation and a monoatomic anion. So the cation in this case is the metal, is always written first and then followed by the anion, which is the nonmetal. So when we are talking again, if you go back to the periodic table and you look, for example, at something like calcium chloride, we always write the calcium, the cation. Remember, those guys always form cations. I'd like you to please pay attention to this, because I've seen people making mistakes and making group 1 and group 2 element, for example, gaining electrons. This never happens in real time, not even in sci-fi movies. These are group 1 and group 2 from the periodic table. They always lose electron or 2 if you're talking about a group 2 from the periodic table. So if you're talking about magnesium chloride, for example, we always write or say the name of the metal followed by the name of the nonmetal. Okay, that's in terms of the nomenclature. So that's for the binary ionic, or it could be ionic ionic with the polyatomic ions. An ionic compound contain a polyatomic ions, right? That's what we're talking about. These group of elements in the periodic table. Now, if you have a question that is crossing your mind, do I need to memorize these? Yes, you do. I will give it to you in the first exam, but I will not give it to you in the final exam, because, and I'll tell you why, because we will mention those and we'll go over them many times, not only in this chapter, but also in chapters to come when it comes to precipitation reaction and balancing equations. So memorizing these and memorizing the charges and the names and also the molecular structure, it is going to be really helpful. It's going to help you later on when you're doing, for example, balancing equation or doing precipitation reaction. So for the first exam, I'll give it to you, and the second, third, or even fourth exam, I expect you all to memorize it. So try to memorize it sooner rather than later. Okay, so let's go back to ionic with polyatomic ions. So again, when we're talking about ionic compounds with polyatomic anions, that means group 1, for example, or group 2 interacting with the polyatomic anions from this chart right here. How do we write this? We always have the cation written first in the formula, followed by the anion. So in both cases, if it is a binary ionic or ionic with polyatomic ions, we always mention the name or put out the name of the cation first, then followed by the anions. We never follow, we never have the anion first, which really makes total sense, because even when you look at the molecular formula, the cation comes first. So just follow the chemical formula. Okay, so this is the structure of ionic compounds, and we talked about it earlier. Ammonium, which is this guy, the first one in this polyatomic ions, and he's the one, and it's the one that only, it's the only one that has the positive charge for this polyatomic ions. That's why ammonium will act as a cation and form ionic bond. Okay, so if you look at the ammonium in this case, so it's the ammonium cation. It is surrounded by the chlorine anions. So ammonium, if you go back to the periodic table, with its single positively charged, it will form an ionic bond with the fluorine, chlorine, and all the other nonmetals in the periodic table. So ammonium from this group of polyatomic ions, ammonium basically behaves similar to the metals in terms of forming ionic bond. So here we are in the exam, and I give you multiple chemical formulas, and you're trying to name them. For example, so first thing you need to do is you need to recognize which one is the ionic compound and which one is the covalent compound. We talked about the covalent, now let's talk about the ionic. So first you'll have to look into your chemical formula and ask yourself if there's any metals in there. If there's any metal, it's a done deal. It's an ionic compound. You don't have even to think any further. How do you know where's the, if it is a metal or non-metal? Then you'll have to look at the periodic table, and this is how you recognize where's your metals and where's your non-metals. I think we talked about this enough at this point. That's one. Or it could also be a metal versus a polyatomic ion. So a metal, again from the periodic table, a polyatomic ion, which means one of those guys in this table, with the exception to the ammonium, because the ammonium has the positive charge, and we will talk about this in a second. Okay, so all these polyatomic ions, with the exception to the ammonium, will react with the metals on the periodic table and behave as an anion, and the metal will behave as a cation to form an ionic bond. Okay, the third type of ionic compounds is ammonium versus a nonmetal, or the ammonium bonding with a nonmetal. Because as I said earlier, ammonium is considered or behaves similar to nonmetals when it comes to forming ionic compounds. So every time, every instant you see ammonium in a molecular or in a chemical formula, you should consider it, or you should consider it just like a metal from the periodic table. In other words, the ammonium will be the cation and the nonmetal will be the anion. As you look here in this table. So ammonium is the only one that has the positive charge, because all of those guys behave as anions except the ammonium will behave as a cation, reacting with the nonmetals in the periodic table, the nonmetals, the oxygen, the nitrogen, the chlorine, the fluorine, the chlorine, bromine, etc., to form ionic compounds. Okay, so please do not confuse this. If you look at a chemical formula and there is ammonium with a nonmetal, it is an ionic compound. Don't please call it as a covalent compound or molecular compound. Okay. The last type of ionic compounds. It could be ammonium with polyatomic ions. So ammonium, which is this one here, reacts with any of these or bonds with any of these polyatomic ions in this table. Okay, so ammonium reacts with any of those guys in this chart to form an ionic compound. So ammonium hydroxide, for example. Okay, so ammonium hydroxide it is considered an ionic compound. In this case, when you'll look at it, you will see there is all nonmetals, correct? Because the nitrogen is a nonmetal, the hydrogen is a nonmetal, the oxygen is a nonmetal, the hydrogen is a nonmetal again for the hydroxide, and you will call it as a covalent bond, and that is incorrect because we're talking about the ammonium molecule as a one entity, and not talking about the nitrogen and the hydrogen separately. So the ammonium behave as cation to form ionic compound. Please keep that in mind. So hopefully when it comes to the exam, no one makes a mistake. So these are the 4 kinds, and this is how you can recognize ionic compounds from covalent compounds. So just like how there is the nomenclature convention when it comes to naming covalent compounds, there is very similar rules when it comes to the ionic compounds. So let's talk about this a little bit, and then we'll do some examples, and hopefully this should do it for this lecture. So naming ionic compounds, we always name the cation first. So when you look at any chemical formula, any ionic chemical formula, you just have to follow the order. So we're starting with a calcium, we're starting with a sodium, with a potassium. So we always put the name of the cation first, okay? When it comes to the cation names, if it is a monoatomic cation, we just use the name of the metal, okay? If it is a polyatomic cation, we only use the name of the polyatomic ion. Example for a polyatomic cation, ammonium. Ammonium is the polyatomic cation, and that's the only one that you will see coming from me during the exam or during the homework. So example of polyatomic cation is ammonium. So when we're writing the name of a molecular, of a chemical formula that has ammonium as a cation, we just write the name of the polyatomic cation, which is ammonium. That's in terms of naming the cations. When it comes to naming the anions, if it is a monoatomic anion, example monoatomic anion, fluorine, chlorine, bromine, etc. Those are monoatomic anions. So those are monoatomic anions. Or for the anions, it could be a polyatomic anion, which would be the name of the polyatomic ion. Okay? Example for polyatomic ions or anions, everything on this table, of course, with the exception to the ammonium. So when you're trying to name those, you will just use straight the name of the ion. So if it is an OH, we'll just call it hydroxide. If it is C2H3O2, we'll call it acetate, chlorate, nitrate, carbonate, etc. That's why you need to memorize those names, and also, most importantly, the charge above those non-polyatomic anions, because you will need it. Okay? In the first exam, you don't have to worry about it. Let's do an example. So when you look at this molecule or this chemical formula, first ask yourself if there is any metals in here, and the answer is yes, there is calcium. Calcium is a metal, because if I look at the second group of the periodic table, here's my calcium sitting right here. Okay, so this is the calcium. So it is an ionic compound, because calcium and oxygen, which is a nonmetal, correct? So it is an ionic compound. How do we name this? For the cationic part, we just mentioned the name of the cation. So if it is a calcium, we just call it a calcium. Straightforward. If it's for the nonmetal, we'll take the root of the nonmetal, which is the same table that we shared or we talked about during the covalent bonding. So the root of the nonmetal, and we just add the IDE to the name of the anion. So that would be ox, IDE, that make it oxide. So it's calcium oxide. Let's do more example. So let's look at NaCl, which we also know, which is also known as sodium chloride. So is it Is it an ionic compound? Yes, because I have a metal, which is sodium. So the name of the cationic part will be just straightforward sodium. The name of the anionic part, we have to be a little bit careful because we'll have to use the root of the chlorine, which is a chlor, and then we add IDE to the end of it, so it will be sodium chloride. Same thing with beryllium oxide. So beryllium, if you look at the periodic table, it's right here in group 2. So it's beryllium, and the root of the oxygen is ox, and we just add IDE to the end, so it's beryllium oxide. Calcium carbonate. Calcium is in the second group on the periodic table, the alkaline earth metals, right here. Carbonate, well, how would I know? Should I name this as carbon trioxide? Of course, no, because the CO3, it's a polyatomic anion. You have to think of it this way. So it's a polyatomic anion. Well, what would I know? How would I know what's the name of the polyatomic anion? And that's where where this chart here comes in handy. So carbonate is right here. So it's polyatomic anion. So that's why it's called calcium carbonate. So the IDE rule goes out the window because we have a polyatomic anion. We'll have to follow the table. Okay? So that's when it comes to writing the name of the chemical formula, or the chemical formula of ionic compounds. Okay? Now let's try to write the formula of ionic compound. And in this case, you'll have the name, and you'll have to convert the name of that compounds into the actual formula. Okay? It gets a little bit complicated in this case, and it's a very tiny bit complicated. Really, not so much work. You just have to pay close attention to this. What you need to do first, you'll have to determine the charge of the cation. The reason why we need to determine the charge of the cation, because it will help us to determine if it is a mono, di, tri, tetra, etc. So we need to know what is the charge of the cation. Then we need to determine the charge of the anion as well. So when it comes to the cation, we can either look at the periodic table, and the periodic table is a great tool when it comes to determining the charge of the cation, because I might have mentioned that quickly, but a group 1 and a group 2, they always have oxidation number 1, everything in here with the exception to the hydrogen, of course, has a positive 1, and everything in here has a positive 2. So anything comes in from these two groups in the periodic table, you should be able to tell what is the oxidation number of that cation, or you can use the table of the polyatomic ion. Okay. For the anion, on the other hand, you can also use the periodic table, and you can use the polyatomic ion chart. Same thing. Well, how would I know what is the charge of the nonmetals of the periodic table? And I think we talked about this extensively. Fluorine, chlorine, bromine, iodine, all those guys, they always gain 1 electron, right? Because they need another electron to reach the octet rule. So when we say they gain 1 electron, that means they're always, always, always found at a -1 oxidation number. When it comes to something like the oxygen and the sulfur, they always exist in a -2. Nitrogen is a -3. Same thing with phosphorus. Carbon is negative. Well, you don't have to worry about the carbon. Okay? So that's when it comes to the oxygen, nitrogen, oxygen, fluorine. Okay, and the halogen groups in general. So this is the oxidation number for the anions, or you can also use the polyatomic ion chart. Then we'll have to balance the charge, because remember, at the end of the day, the molecular or the chemical formula, it has 0 net charge in total. It's all balanced out. The positive charge with the negative charge, they both cancel out, and there is no excess of neither the negative charge or the positive charge on the overall molecular formula. Okay? Then you will write the corresponding formula. Okay, so all these 4 rules, let's put them together. Put all these gears together and try to do some examples. So let's determine the chemical formula for something like magnesium chloride. So I know from looking and doing so many tests before, general students will get so intimidated when they see the name. Oh, magnesium chloride, forget it. I'm not going to be able to. I'm not even sure what is magnesium. Um, but that's not the case. You'll have to look at the periodic table, determine what is your oxidation number. Generally, the periodic table will have the name of the elements, and I think the periodic table I'll be giving in the exam will have the name of the elements as well. So it's a very easy peasy. So first we'll have to look at your cation. Number one, I'll have to determine the charge of my cation. That's the first thing you need to do. So locate your element in the periodic table. If it belongs to group 2, like magnesium in this case, then I will know all the elements in group 2 in the periodic table, and the alkaline earth metals. All these elements will have a positive 2 um, charge, always as cations. Chloride, on the other hand, just like how I talked about this earlier, chloride, along with the other halogens, they always have a negative charge. So I have 2 positive charge for the magnesium, a negative charge for the chlorine or for the chloride. Okay, so it will be 2 chloride and 1 magnesium. Now, you can think of it also this way. So you have 1 negative charge and you have 2 positive charge, correct? In order to balance out the positive charge on the magnesium, which is positive 2, I will need 2 negatively charged chloride in order to cancel out the 2 positive charge. So in total, I will have a net of no negative charge, right? There's 0 charge. Do you see any positive charge or negative charge over this molecular or this chemical formula of magnesium chloride? No, there's no charge at all. So the magnesium, so you need 2 chloride in order to cancel out the magnesium, the 2 charges of the magnesium. I'll give you another way of looking at this shortly. Sodium sulfide, same thing. So sodium, I know always sodium has a single positive charge or 1 positive charge because it belongs to the alkali metal in the periodic table, group 1. When it comes to the sulfide, sulfur down here with the oxygen always needs 2 electrons, so it's always a negative 2, so it's Na2S. So you will need 2 of the positively charged particles of the sodium to cancel, in order to cancel the 2 negatively charged 1 anion of the sulfide, okay? So if you have 2 negative, you'll need 2 positive. If you have 2 positive, you'll need 2 negative in order to cancel out, right? For the potassium chloride, potassium always has always a positive 1, right? It's right here. And iodide is down here, so it's a negative 1. So when it comes to potassium chloride, it's Ki, okay? Because you have 1 positive charge, 1 negative charge. They're happy together. You don't need to more of the chloride or more of the iodide, because the negative and positive charge, they cancel each other out. Calcium nitride, same thing. You have calcium, which belongs to the second group of the periodic table. Nitride has a negative 3 all the time. Then you will have 3 of the potassium, 2 of the nitrogen. Another way to look at this, which I think you guys would love this better than looking at it from neutralization of the charges. You can basically swap the charges of the cations and the anions. So going back to our example of magnesium chloride, I have 2 positive charges on the magnesium, and I have 1 negative charge of the chlorides. So if you do the swapping, the 2 will go down to the chloride, and the 1 will come down to the magnesium. So it's MgCl2. Remember, the 1, we don't write it down, right? It's always assumed. When it comes to the calcium nitride, you have 2 over the calcium, and you have 3 over the nitrogen. So the 3 will come down here, so that makes it calcium 3. And you have 2 of the nitrogen. Okay? Let's do sodium sulfide. So you have 2 negative charge. That one will swap, will go down to the sodium, and the positive charge will go down to the sulfur. So there's only one of the sulfur and two of the sodium. The Ki, it's 1 versus 1, so it's Ki without any subscripts. Okay? When it comes to the polyatomic ions, you would basically need to follow the same concept. So you will have to find out what is the charge of the cations, find out what is the charge of the anions, and again, it's either the periodic table or the charge for the polyatomic ions, and you just have to swap the charges of the anions and the cations, okay? And it's very simple. So, for example, if you look for the calcium nitrate, for instance, so the nitrate, if I go back to this table, okay, so the nitrate, which is right here, so the nitrate has a negative charge, one negative charge. Now, if I come down here to my example, calcium has two negative charge, right? So let's do this example here. So calcium is 2 positive, right? Nitrate has 1 negative. So what happens, you swap up those charges. So it's going to be calcium, and you open parentheses, and that will be NO3, parentheses 2. Because that 2 that comes down here, it goes for the polyatomic ion, the whole polyatomic ion, and not for the oxygen only. So that's why we call it NO3, parentheses 2. Okay, let's do another one. Let's do the ammonium, for example. So if you go to ammonium, let's do this one right here. So ammonium, for example, NH4, has a positive charge. Carbonate has 2, so NH4 positive has a negative 2. So what we do, we swap up the charges just like this. So it will be ammonium, NH4, 2 carbonate. Okay? That's when it comes to doing polyatomic ions. Cations and anions, obviously, because ammonium in this case is the cation. So I think this brings this unit to conclusion. Let's do a quick review, go over what we have been talking about for the throughout this unit. So we talked about covalent bonds and we talked about ionic bonds, correct? When it comes to the covalent bonds, we have 2 different classifications for this. We have the non-polar covalent bonds when we have two atoms of the same kind, something like H2O, O2, F2, Cl2, etc., bonding together, and you have no excess positive charge on either side or negative charge. So in this case, you have the electron cloud right in the center between the two atoms. So there's no significant charge has been formed, and there is no polarization in this kind of bond. So each atom attracts the electrons equally, and the electrons are centered in the middle between the 2 atoms. Okay, so the electron does not lean on either side of the atoms because both atoms are essentially the same. Or we can have a polar covalent bond, and in this case, you will have polarization on this bond because one atom has more electron affinity than the other. So it will drag more electron density on one side than the other, which would result in a partial negative charge on one side and a partial positive charge on the other side. Okay? The ionic bond, on the other hand, it's a complete transfer of electron. The covalent bond, it was sharing of electron. Ionic bond is the transfer of electrons. So electrons transfer from one atom to the other, forming a positively charged particles, aka cations, and negatively charged particles, which is also known as anions. The positive and the negative then bonds together to form the ionic bond. In summary, when it comes to molecular compounds, which we also refer to as covalent compounds, molecular compounds are nonmetals to nonmetals combination. And it's also, which also forms the covalent bonds, evidently. And sometimes we might have molecules that has covalent bonds, correct? Like the polyatomic anions that we looked at earlier. Ionic compounds, on the other hand, it's a metal to non-metal combination, or it could be also a polyatomic ions combination, like the ammonium when it comes to the polyatomic cations, if you want to call it, and also the polyatomic anions, which is from the table that we mentioned earlier. It forms ionic bonds, of course, and the alternating cations and anions in a crystal. So it basically it has a crystal formation where the cations and the anions, they surround each other. Okay. Chemical nomenclature, I think we talked about this enough at this point. This table here summarizes all the rules that you have to follow. And I think everything should be clear at this point. So I will be posting, of course, homework for this. If you have any questions, do not hesitate to email, and I'll do my best to explain further.